Why do we need deep CNNs? There are multiple reasons, but one important reason is the receptive field. The kernel size of a typical convolution operation is 3 by 3, which denotes the receptive field of a single layer. By building deep CNNs, our network's receptive field increases incrementally. This helps our network model long-range dependencies. Standard CNNs are designed to have a large theoretical receptive field. For instance, ARSNet 50 has a receptive field of 483 pixels, which is more than enough for the standard 224 by 224 input resolution. However, this receptive field is not enough for high-resolution medical images. For instance, a mammogram has an input resolution of around 3500 by 2500 pixels. This means if we use an expensive ResNet with 200 layers, we still won't cover the whole input image. Obviously, a different solution is needed. This is why I'm glad to present our paper, Deep is a Luxury We Don't Have. I am Ahmed Taha, a research scientist at White Rabbit AI. CNNs are great. They have a high inductive bias, which is optimal for images. They are ideal for capturing low-level details such as edges. However, they suffer when modeling long-range dependencies. For a high-resolution input, a huge number of convolution layers is needed to cover the whole image. In contrast, transformers are ideal for modeling long-range dependencies. Theoretically, the entire input signal can be covered by a single transformer layer. But transformers are expensive. A single attention layer computes the pairwise similarity between every query and key token. This has quadratic complexity. For a high-resolution medical image, the number of tokens L is large. Accordingly, a vanilla transformer is not a solution. Fortunately, building efficient transformers with linear complexity is an active area of research. Through these efficient transformers, we can process high-resolution medical images and model long-range dependencies. In our paper, we compare the pros and cons of different efficient transformers, such as reformer, longformer, and performer. We end up using performer for its simplicity. Performers regard the attention mechanism through kernelization. From this perspective, the softmax operation is a kernel that can be approximated using random feature maps phi. This enables us to change the order of matrix multiplication and to compute self-attention with linear complexity. To leverage performers for medical images, we propose an attention convolution AC block. The AC block combines the benefits of both attention and convolution operations. The AC block enables downsampling as the network depth increases. Furthermore, the AC block both consumes and produces spatial feature maps. This layer integrates seamlessly into various vision architectures designed for different tasks, for example, classification or detection. While it is possible to use AC blocks to build an entire network, recent literature highlights the importance of pure convolution operations at the early stages. These early convolutions increase optimization stability and improve generalization performance. Accordingly, our high-resolution convolution transformer architecture, HCT, leverages convolution blocks at early stages and AC blocks at late stages. We evaluate the HCT architecture using a high-resolution mammogram dataset. We report both the AUC and the 95% confidence interval. With performers, HCT always achieves superior performance. Besides this quantitative evaluation, we evaluate the receptive field of our network qualitatively. This figure shows the effective receptive field of a pure CNN architecture versus HCT. We evaluate the effective receptive field using 100 randomly sampled breast images. HCT is superior to the vanilla CNN. HCT learns to focus on the breast's location without explicit supervision. We perform multiple ablation studies to identify the strengths and weaknesses of HCT. Throughout multiple studies, we observe a consistent pattern. HCT brings minimal boost, if any, whenever the malignant tissue is small. For medium and large malignant tissues, HCT brings a significant performance boost. This aligns with our intuition that a high receptive field would be beneficial for tissues that require global information. Finally, we evaluate whether high resolution is indeed needed for better performance. We measure the performance of different architectures using half and full resolution inputs. By using the full resolution, we boost the AUC of different architectures by more than 4 points. This evaluation emphasizes the importance of processing medical images at their original high resolution. Finally, we are glad to announce that we released our code on GitHub.